mic's up. Hopefully you can hear me and we're not muted or anything. Yeah, welcome to today's Open Neuromorphic seminar. We don't have Fabrizio or Gregor with us because we're on the Australian time zone, so this is special for me. But yeah, no, we're lucky enough to have Toby here. We've been following Toby's work for a pretty long time. He's a senior lecturer at the Queensland University of Technology. He's been doing some incredible work on making robots less stupid. I'm just going to leave it there. I'll let Toby talk about how awesome his work is. But yeah, take it away, man.
Perfect. Thanks so much for the kind introduction, Jason. And it's great to being here, and it's special for me as well because of the time zone difference. I typically can't make it to the Open Neuromorphic workshop, so it's great being here live and in color. What the plan for me is today is to mainly talk you through one of my papers on event-based vision and how we make it nice and fast and super simplistic, which I particularly like. But before we get there, I just wanted to give you a brief overview of how I got to where I am nowadays. So if you want to check me out on LinkedIn or GitHub, Twitter, etc., my handle is typically Tobias Robotics. And I'm originally from Germany. Grew up there in the small green heart of Germany, they call it. Nothing around, no big cities. So just a country boy. Studied there, so I did all my education there, basically. My undergrad in a small uni in Ilmenau, which probably even Germans don't know. And then got this really cool opportunity. I was always open to basically go overseas, go abroad. I was in Singapore for a while, which isn't on this slide, did an internship. But really my academic journey led me to York Uni. And I worked with John Tsotsos, which some people might know. He's a big guy in visual attention, active vision, that kind of research, and that really shaped where I am those days and what my thinking around robotics and all the neuromorphic things are as well. Spent some time there, met my nowadays wife, and then we followed each other around the globe. So I did my master's at the Uni Edinburgh. Studied AI, but really what I studied is vision. So back in those days I was a vision guy, computer vision, computational neuroscience of vision, vision from the psychology perspective. So I guess that shapes me up until today. So my background really is in robotic vision, and then I'm a fairly new neuroscience and neuromorphic person there. And then I got to do my PhD with Yanis Demiris at Imperial College London, and that was on basically perceiving humans in human-robot interactions. So I did a bit of work on gaze estimation, perspective taking, blink estimation, all of this kind of stream of work. But I was always really interested in the bio-inspired / brain-inspired way of how humans perceive the world, and that then I wanted to map to computational models for robots and see how we can come up with similar general models of the world in the robotics context. And then I ended up at QUT working as a postdoc with Michael Milford, because his work on robot localization with bio-inspired principles has really interested me in my PhD, and he was one of the people that I cited the most in my thesis. And then he came over to London, and we had a good chat. And then there was this possibility for a postdoc, and then that was quite a few years back. And since then, I got a permanent tenured position here at the Center of Robotics, and I'll tell you a little bit more about this really, really cool center later on today. Now, let's dive into my main kind of research that I'm doing those days, and that is on visual place recognition. And I'll tell you what that is, and I will also tell you why I think it's really, really cool for the Neuromorphic people, and hence I'm here at the Open Neuromorphic workshop. So what is place recognition? We want to match a query image, which is taken by a smartphone, a robot, anything you can imagine, AR, VR, to some reference image from the same location. So why is that cool or useful? I'll tell you in a second, but if you look at those images on the right-hand side here, you can already get a sense that it might be a really difficult task because a lot of the parameters can change. So at the top, there's a lot of appearance change from daytime to nighttime. At the bottom, we have a heavy viewpoint change, and we might want to estimate the pose of the query image relative to the reference image. And at the bottom, there might even be seasonal changes over time if you look at outdoor environments. And that's something which has increasingly interested me, and I'll tell you a little bit more about that later on. Those place recognition algorithms are incredibly good those days in those urban scenarios, but I think we have to catch up. And being in Queensland at the moment, in rural Queensland, the algorithms don't work nearly as well, but they're equally needed. And place recognition has many, many use cases. So if you have a little bit of a robotics background, you might have heard of SLAM, so simultaneously localizing and mapping, and we need it there as a loop closure component. We might want to relocalize a robot if it's being shut down and restarted somewhere else. And I already mentioned it, why it's difficult, because of various things. For example, perceptual aliasing. So perceptual aliasing is the problem where places that are geographically different might look very, very similar. So you might have heard of the many replicas of the Eiffel Tower, which all look like the original one in Paris, but there might be somewhere completely elsewhere and look more or less the same. Another difficulty is that the maps can grow in size. If you're basically looking at a world scale mapping solution, there's a lot of maps that you need to store. And if you ever installed Flight Simulator or something like that, back in my days, I had, I don't know how many CDs to get like a super low res map of the world, and that is just increasing in sizes. And what I'm particularly interested in is those resource and computational and storage constrained systems. So small robotic systems, hexapods, drones, etc., where you can't just throw your latest GPUs on. And if any of that sounds interesting to you, we recently published a tutorial paper in the Robotics and Automation magazine, which is called Visual Place Recognition, a tutorial. It serves both newcomers as well as established people in the field, and we kind of nicely, I hope, motivate the whole topic. So please check it out after if you'd like to. Well, visual place recognition is all well and nice, but why would we want to do it with neuromorphic principles? And why is it particularly interesting from my opinion for the neuromorphic use cases? So one of the cool things is that we can easily and meaningfully scale the task difficulty. So if we leave autonomous vehicles aside, there's many use cases where you might not have the super drastic changes in appearance and viewpoint. There's many use cases where some simplifications of the task could still be deployed in real-world deployments. The data set size can be adjusted meaningfully as well. So you might not always be interested in a world-scale model. It might be enough if you want to localize in, like your university or company building. We heard a lot, vacuum cleaners are the most deployed robots around. So, from small scale environments all the way up to super large environments. And place recognition techniques are amenable to many strategies, such as attention and hierarchical strategies. And there's been a lot of work by the neuromorphic people in those areas. So it would be interesting to deploy, to use some of them in the place recognition context. And then I already mentioned it, because of the robotic deployment, oftentimes power consumption is important and latencies as well. So sometimes it might be the case that if you have reduced energy and power consumptions, then that would enable you to completely go in different environments because of the larger deployment times that a robot has, which is, I think, super cool. So how do we do it? What's the gist of the paper that I want to talk you through today? So it's event-based visual place recognition. I guess I don't need to tell you about event cameras. Just very brief primer. So as opposed to conventional cameras that have fixed rate samplings in time, we basically sample changes in the environment with those event cameras. So if there's fewer changes, then fewer events. If there's more changes, like here, this crazy dot moving, then we get this really, really nice event stream in time. And they have super nice properties with regards to the high dynamic range, lower latencies, and energy efficiency as well, which is really, really nice and cool. And that's what we use in this particular work that I'm hopefully going to guide you and implement with you, which will be interesting because it's the first time for me that I do this kind of joint coding exercise. So hang in with me. Hopefully we'll get there. Before we get to the coding though, I want to briefly talk you through some of the related works for this particular paper. So the main paper, just to preempt a little bit, is basically using just very few pixels out of the 100,000 pixels in a Davis 346. Just using very few pixels of those and comparing the event stream binned over a certain time window between the reference and query times. So at reference time, we map the environment basically. At query time, we want to recognize where we've been before. And ideally, those event streams should be similar when we revisit the same places. And what I'll show you, hopefully, is that we can come up with a very simplistic way of doing this, which is still very high performing, and most importantly, super, super fast. So when I started out with event-based place recognition, I started with this very first work listed here, which basically reconstructed conventional frames. And then we used a standard place recognition technique called NetVLAD. And we did it in some cool way where we didn't use a single reconstruction, but we varied the parameters of the reconstruction at reference time, which led to a high-performing system. But the drawback, of course, is that even at query time, you need to reconstruct those frames, and it can be very slow. And then run it through a deep network as well. So, you can imagine that there's quite a few disadvantages and drawbacks. And the same goes for some other nice papers by other folks in the field, which similarly use that NetVLAD, which is this technique for place recognition, and some kind of different event representation. So on a voxel grid representation, or after estimating edge images using the event stream. So this is basically what's in there, and they all introduce delays. Now, the work that I'm going to tell you about today, we use a very sparse representation. So by sparse, I mean very few pixels over the image coordinates. But we want to use varying pixels. So by those, I mean the pixels that have the highest kind of changes over time, because they are most likely the ones that are the most interesting for place recognition. So we don't want to have a very, very flat event rate, because that's not going to tell us anything about the place we are in. And if we do that, we can do frequent and computationally cheap estimates, updates of the location estimates. And this is where I'm going to jump in now with my code notebook, and hopefully I will find I'll find it somewhere. So just hang in with me for a sec. Here we go. Okay, so hopefully you can, yes, you can see what I want you to see. Perfect. And okay, cool. So what's happening? Basically, I'm going to guide you through a stereotypical visual place recognition pipeline. And hopefully it will show you that you can get kickstarted super easily and have lots of fun with place recognition. So it's, like a nice topic to get into quite easily, but still make meaningful progress in certain ways. So I hope my font size is big enough. Let me make it just a little bit bigger. Okay. So first of all, thanks to all the people out in the field who come up with those amazing libraries. Here I'll use Tonic just for ease of use, but there's so many cool libraries, and I'm going to talk about some of them later in my talk and how I make them easily accessible via Conda. But that's to come in a little bit. Now, I've cheated a little bit and implemented some helper functions which are a bit boring. So just to talk you through, the first one is just to load the event streams and kind of let them start at 0, 0. So I'm just going to load the new pandas, printing some metadata, and then that's some plotting functionality that we will need later on just for ease. But I'm just going to run it and hope that it works. And I should tell you that as well, if you go on my GitHub and search for the how many events do you need paper, the talk notebook is available there as well. So if you want to open it up on GitHub and play with it while I talk, feel free to do that. Okay. Now, let the fun begin. What are we doing first? First, we will load the event streams. So we need 2 of them, right? We need the reference event stream, which is just this one which I collected at 8:25, and then a query event stream, which for ease here is basically collected. Just basically, I finished one, and then I collected the next one. So it's like a super simple event stream. I'll show you what they actually look like in a second. Now, let's first investigate a little bit what they look like. So, they're both roughly 165 seconds long, and I basically traversed the QT Center for Robotics twice, roughly in the same speed, same manner, basically everything the same, just slightly remote operated, so there will be some differences there. And what I'd like to do first is that we take a look at the event frame representation. So I'm just going to come up with a typical frame representation. So let's implement a transform, and let's do, I don't know, let's just do a crazy one for 1 second, okay? And thanks to Tonic, that's really, really easy to do. We just give it a time window, and I think the time window should be in millisecond, in microseconds. So there's some factor missing there. And then using that transform, we can now transform our query and our reference. Whoops. All right, okay, here we go. Here where we start. It's 2 frame, not event frame. GitHub Copilot lets me down, but that's okay. We'll get there. All right, and now we have those event frames. Let's look at them, okay? So that I'll copy from elsewhere just for ease. So we can look at it. And I should, okay, so this is over a really, really long accumulation window of 1 second. which is probably not what I should be doing. Let me create another one. Maybe have a more reasonable time window. So just 66 milliseconds. And then let's have a look at that, so you can get a better idea of the data that we are looking at. Obviously, need to run it again. And then we'll have, cool. Okay. So now we can scroll through the data. And I don't know why it shows up twice. But that's okay. Okay. So this is what it looks like. Okay, those event frames. And basically, to give away what you are seeing here, you see a robot moving forwards, but with a side-facing camera. You basically see it moving around the environment, and the visualization isn't particularly nice, but you should get the gist that you basically, there's some windows here, some cool patterns on the wall that you can see. So they should be quite uniquely identifiable, which is exactly what we need for visual place recognition. So if you look at that, basically, you wouldn't see those patterns on the wall everywhere. And that's important for place recognition because they are unique place representations, basically. And what we will attempt is to come up with a representation where we store those unique, somehow represent those unique places or uniqueness about a place. And then we can recognize it later on with query frames. Okay, now let's basically investigate a little bit what the event rate looks like over time. So what we can do is, I think I already implemented one of those helper methods. Basically what it does is just, it's showing you the mean number of events per pixel across those 66 milliseconds over time. So as we've seen earlier, like our traverses are roughly 165 seconds long. So that's what we see on the x-axis, and on the y-axis we see the mean number of events. And when I started out with this work, basically I was like, oh, okay, that's interesting, because there's quite a big variation over time, and that's just looking at the sum basically of all the pixels that are out there in the environment. So you can imagine that at different times, at different places, basically, some pixels or some pixels will have higher event rates than others. So this is really, really cool. And the first question that I asked myself is basically, how does that change when we revisit a place? And this is what we see in this graph here, okay? So in blue, we see the reference, basically the reference event rate. And in orange, we see the event rate when we revisit those places again. And what we can see is that, like there's a strikingly, like nice match between the two. So I thought, with my signal processing hat on, there should be a way of quite easily recognizing those places, or not easily, but potentially being able to recognize those places again by just looking at the number of events that have occurred in certain time intervals. And as I will show you later on, if we do it in a smart way, we can do it basically super, super rapidly, which is what we intend to do in this particular work. So what that basically means is, okay, so this was the first research question that I just went through, and that is, can we describe, no, that's not yet the research question. So the first research question, which I will code up in a second, is, can we describe a place in a storage and computationally friendly manner while still achieving high performance? So far, we basically used all the pixels as you would do typically, but I'll show you in a second that there might be a cooler, nicer way of doing that with just very few pixels. Okay, so in order to do that, obviously, we'll need to, let's just pick some random pixels, okay? Let's pick random pixels, and hopefully Google Pilot, let's say 100 pixels, okay? And let's do it like super simply, okay? I'll create an empty list, and then for, we want to draw basically a random integer, which is, any of the pixels basically. And rather than using the Copilot suggestion here, which picks X and Y independently, I'm just gonna pick a index here. So let me just code it up quickly. Okay. All right. So what are we doing here? Except for throwing some hang in there with me. No, okay. So that's cool. Okay, so first what we're doing is that we're looking at basically just grabbing any pixel, like index, and that's flat, so across the whole image range, and then we can unravel that to basically get the actual XY location. Then we can append that. Okay, let's see whether that worked. Let's print random pixels, and okay, it looks like we've got 100 random pixels here. And now what I'll do is that I'll just plot those random pixels to see where they ended up on the image plane. Okay, perfect. That looks okay. So we get like a fully random distribution here. One of the cool things that I'll show you later on is that we can intelligently pick those pixels and increase place recognition performance. But for now, let's just go fully uniformly randomly. And now what we want to do is that, as opposed to creating our frames here using the whole image and all the pixels, we want to do the very same things and converting only the 100 the events that occurred at those 100 pixels. So we already have the event frames for all the pixels, and now we basically want to subselect the ones for those 100 pixels. So how can we do that? Let's create a new method, create event frames of the subset, where we use the event frames that we already have and the random pixels that we just generated. Okay. And one of those frames will basically have the, let's just initialize it and say, all right, we want to have it of the dimension of the number of frames and the number of random pixels. So I hope that makes sense up to this point. So just using a subset. And now what we can do, Copilot is smart enough, I hope, is that we just look at the all the frames that are coming in, and then we look at the frames at the pixel location that we picked above and put it in our frames subset. And that assumes that we just have a single count. So at the moment here, we see that we have the positive polarities and the negative polarities as we are used from event frames. But here, let's just ignore the polarities, okay? And how can we ignore the polarities? We're just going to sum over the no polarity, we just sum over the polarity dimension with numpy. So I hope that makes sense, and it's not x is 1. Okay. And now we can create those event subsets. We just call the method, basically, which hopefully should work. Random pixels, query. Let's just... Okay, let's see whether that works. No, it doesn't work. That's okay. I'll have a look at my cheat sheet. How we get there. Zeros. All right. Shouldn't happen there. All right, let's have a look at this first while we are debugging it. And okay, that looks all right. So we've got the number of event frames times the image dimension. So everything is good there. Let me just, in the interest of time and getting that to work, I think that's just a... Oh, yeah. All right, I got my brackets wrong. And now we have the issue that I always like to swap. So here, I reckon we just do a JI, and then we should be... No, we shouldn't be good. Here we've got our issue. Perfect. Okay. And now we've got this random subset of pixels. And now let's plot this again. Okay. Let's see what happens here. So what we're looking at is why? Give me 1 second. Let me just understand what's going on here. All right. Okay. Just needed to run it. So basically, let's step back for a second. What have we done? We created this subsets of those events, and now I'm plotted the same as above here, where we looked at the trend of the event rate over time, but just using 100 pixels. And why have we done this? Because if you want to store the place representations, it's much cheaper to store just the event count that occurred at, let's say, 100 pixels here, as opposed to the 90,000 pixels as in the original image. So there's like a tiny percentage of storage that you require for that. And what we see in this graph here is that although we just used a tiny subset, this observation that I told you and hypothesized previously, that the trend at reference and query time is still going to be very similar, despite using just those tiny number of pixels. So that's pretty cool, I hope. And I don't know, Jason, whether we've got any questions so far. No, all good. Cool. So, and what we can also show here is that this trend is super representative between all pixels in the 25, or like here in this case, I showed just 25 pixels. So if we show, if we plot this trend over time, we'll see that there's a remarkable similarity despite this heavy subsampling over space. Now, let's go to the second research question. And that is whether the dynamic change observed by traversing through a place remains relatively constant when we traverse this. And I think that's what I've already done and already showed you. And here it's in nice slideshow form, a little bit nicer than what I coded up, but it's basically exactly the plot that we've seen previously. So that's really cool, because the profile of this small subset is highly similar between query and reference traverses. So this is exactly what we want for place recognition. And now we're asking ourselves, are some of those pixels more discriminative than others? So what I'll show you in a second is that basically, just to preempt it, you can actually recognize those places using a very simple technique to rediscover the places. Let's maybe do this first in the coding session, and then I'll show you that actually, hey, cool, we can find, rather than just randomly and stupidly picking pixels, we can use an intelligent subsampling. Okay, what do we need to do next? We somehow need to associate each of the query places. So as the robot traverses again through an environment, we need to associate that with one of the reference places. So we basically need to decide, has the robot been at this place before? And if so, at what place has the robot been before? And how are we going to do that? We are going to do that by looking at the sum of absolute differences for across those 100 event counts that we just looked at. Okay, so let's step back. Basically, let's look at the very first query frame, right? First query frame. What is that? Okay, so here we got our representation of the number of events that have occurred across those 100 frames in 66 milliseconds at query time. And you can see that in most of those pixels, nothing has happened, and then at some of them, a bit has happened. So this one was our winner with 6 events in those 66 milliseconds. And now we need to compare that to all of the reference frames that have occurred. Okay, so find best reference match, reference frame. Okay, and how do we do that? No, we don't do it like that. Let me tell GitHub Copilot, use sum of absolute differences. And okay, this is exactly what we want. So what's happening here? Okay, so we basically, for this query frame, we look at each of the reference subsampled frames, and then we just look at pixel location 1. We had an event count of 1, and let me just show you the first reference frame as well. All right, okay, so here, and now we're basically summing up the differences, okay? So 1 minus 3 is minus 2, the absolute of that is 2, so 2 plus 0, so there was no difference here, plus 0, etc., etc. And then here we will have some differences. So that's our unique descriptor. And then we can, sum them all up for all of the different reference frames. And the best reference frame is the one which had the lowest sum of absolute differences. That's the idea here. And for this case, we need to have one of the query frames. So let's just say the first query frame, and then all of the reference frames. So and that will, okay, so here in this case, the best matching index is 1844, which is not the correct match. That's an incorrect match. The correct match would have been close to 0 because it's the first query frame. So we were hoping, because those two traverses are exactly aligned, that we get an index which is close to 0. So here we have a false match. But that's okay, right? We don't want to have that. And actually what I found is that using very, very short tiny accumulation windows, such as 66 milliseconds in this case, doesn't work really well. So I have increased the times to, let's just say, 1 second. So you might think that goes against all the neuromorphic principles that we learned about and all the low latencies, etc., that we want. That's correct and that's incorrect, right? Yes and no. So basically, to come up with, like a good, unique description, you will need to that there's no instantaneous recognition of a place with an event camera, unless there's always some dynamic objects at that place. Instead, we'll always need to look at some accumulation in whichever way we want to do that. Here I use the most simple way of event frames. However, what we can do is, because that calculation of finding the closest, like the best match in the reference index is so cheap, you can basically do that really, really frequently. So you will need to use 1 second to define what the place is, but you can have a sliding window approach, where, as opposed to just saying, okay, I wait 1 second and then I wait for the next second, I wait for the next second. Each couple of 10 or 100 microseconds, you might want to update your estimate of where you are. And that you can do because it's very, very simple to compute this best match. Okay, I hope that that makes sense. And what I'll show you now is basically a distance matrix, and I'll swap out. I'll cheat here, and I'll show you this distance matrix. So what is that? Basically, what I computed is that sum of absolute difference between all the query frames and all the reference frames. And ideally what that would look like is that we have the, and let me just remove this for a second. Okay, so I don't know how well you can see it on your screen over the streaming platform, but there's this faint dark red line, and dark red here is like close to 0. So that indicates a better match. Ideally, what we would like to see is this diagonal in the distance matrix. So what does that mean if there's a diagonal? It is, like add a particular query frame. So once the robot traverses the environment again, we know that the best match is roughly at the reference frame of the same index, because we traverse the same environment with the same speed, everything basically keeping the same. And in the paper, I obviously generalized that quite a bit to different velocities as opposed to going for fixed temporal window sizes, looking at fixed event counts to create the event frames, etc. But this is basically the ideal here. And then what I've plotted here in those with those blue dots, and here let's just look at this where I use the 1 second windows, is the best match. And you can see that the best match is more often on or not on this diagonal, which is exactly what we want. So there's like a very super simple proof of concept for visual place recognition with event-based vision subsampling. And then we can basically look at the results. So we can define what is the ground truth. So here you just say, if the matching place is somewhere along this diagonal, let's consider it to be a true match. Otherwise, it's a false match. And then we can calculate the accuracy, and it's around 70% for a window size of 1 second. And then you can basically implement it with the sliding window approach that I previously talked about, which is, I think, quite cool. But okay, so let's jump back to the PowerPoint, and I won't, in the interest of the time, I see I think I'm running a little bit behind time. I just want to show you one cool thing what we observed. and that is that we can, rather than uniformly randomly sampling pixels, we can sample them according to the variations that happened at a particular pixel location across the reference traverse. So what you see on the right-hand side here is that the darker red here indicates that there was a higher variation in the event count for this scene. And now, typically, if you were in person, I would ask you what you think was recorded in this particular reference sequence. So I'll just give you, like 10 seconds to have a think what you think is shown there. What kind of environment did I traverse? Oh, Jason wants to have a go. Yes, please, Jason.
The go that I want to have is, do you want me to do a 30-second countdown and end it at 20 seconds?
No, that's good.
I'll let you.
Any idea, Jason?
No.
No? Okay. So that's me driving through a beautiful suburb in Brisbane during COVID, because I wasn't allowed to go into QT. And what you see basically here very faintly is the bonnet of my car at the bottom. And obviously there's zero variation in the event count, because it's just, the event camera statically observes and there's no change there. And then the road here, there's a very low variation as well, because the road is always blackish. And then on the sides here, there's like tree lines and street lights, etc., etc. So there's a higher variation on the sides of the roads. So what you basically want to do is heavily selecting pixels which are in these interesting regions, and only very sparsely select them here at the bottom. And obviously there's some false matches. For example, here, like this, some vibrations on the bonnet where some of the pixels were selected, but that's okay. And what happens then is, if we now look at the random pixel selection that I just showed you earlier in the code session, where we achieved those 60% for 100 pixels, which is exactly what we ended up here. So that's a good replication of the paper. So I'm very happy about that, because that's the first time that occurred to me. What we can do is, if we use this proposed pixel selection, we can bump the performance by, like 15% absolute for those low number of pixels, which I think is quite cool. And then the reviewers asked us, rightfully so, what happens if you just, that there's the bonnet in the bottom third of the image. What happens if you exclude pixels there? This is what's shown in green, and this is basically working a little bit better than the random pixel selection, but not quite as good as our proposed pixel selection. We already went through the methodology here, and here is, Peter Cork, who just recently retired from the Center for Robotics, unfortunately, but this is, the environment that I told you about previously, and kind of the event frames that you would have seen as well. So in the interest of time, I'm going to skip over those couple of more ablation studies, and basically, like, just to show you the results. Our results here are shown in brown, and it's a precision recall curve. So for those people who haven't seen them before, ideally you want your method to be in the top right corner, which is like the perfect condition. And what you see is that we don't perform as well as our previous technique, which is like the red one here, but we are 1,000 times faster in processing compared to that previous technique, and basically perform similarly to all the others, while being much more storage and computational efficient compared to those other techniques. And that's for multiple data sets. So that is my, that's the first kind of paper and code session there. And I think I want to take some questions, if there are any at this point, and then I'll talk you through some of the other cool stuff more on the spiking neural network side after that. But if there are any questions, please let me know.
Yeah, it's a quiet crowd because I think Europe is asleep.
Yeah.
But yeah, you alluded to sparsity at some point. I'm wondering, have you done any analysis of how sparse representations can, and I guess spreads across how sparse the events might be and how they might impact the performance of these algorithms?
Yeah, absolutely. So you can do some theoretical analysis, basically, as to how it basically depends on the distinctiveness, on the uniqueness of the places that you visit, and how long your accumulation time needs to be, and how few pixels you need. So there's like when you think about it a little bit, you can basically, look at what do the typical variations look like during reference time, and the higher those distinctions, and that will depend on the sparseness, obviously, the fewer pixels you need, and the shorter time windows you need. And then once your environment becomes larger and larger, there is a high chance that you will have this perceptual aliasing that I talked about previously. So then that means that your performance will drop more and more. One of the things what we did in the paper to somewhat counteract that is to look at sequence matching. So as opposed to matching individual event frames, you then match multiple consecutive ones. And then that basically kind of goes against the trend of the sparseness that you talked about, because you have a more distinct representation when you look at videos as opposed to images.
Gotcha. Also, just trying to project what other questions Gregor would slam you with loads. Trying to think of what he would ask.
Yeah.
So this is maybe like a selfish curiosity thing.
Yeah.
So you're projecting events into frames. Is there much work done in treating the events as just continuous, like the default tuple representation? I know that with the deep learning crowd, some people have tried it and then they quickly gave up because it's just not a natural way to make sense of information. Same deal in visual place recognition?
If you wait till the second part of the talk, I'll point you towards progress that we are making there. We are absolutely believe in that principle, and I hate the in the second part of the talk you will see we started out with conventional images and used some Poisson spike representation to convert them to spikes, and then did stuff there. And I was like, we are crazy, like we've got the event-based pipeline, then we stop and we have the separate spiking-based pipeline. What are we doing? And recently my postdoc Adam came up with a nice methodology of having a fully event-based sensing and processing without conversion to some other event frames, voxel grid presentation, whatever else is out there. And I'll point towards that in the second part. It's not yet published though, but hopefully it's just going to be a matter of a couple of weeks, months before the archive paper.
Nice. That's awesome. Very excited for that. I see another question. Say hi to him from me. I saw him. Last I saw him was a few years ago at a bar in Canberra, I think. Question from Paul. Paul's asked, so what is the use case of the matching? Do you need to see the full scene to match? Or how many events do you need to acquire? Could I identify where I am partway in a run?
Yes, absolutely. So do you need to see the full scene to match? No, you don't. So really what we are interested in, and what I point towards in the paper as well, is that this heavily subsampled scene is sufficient. That's really cool for a variety of reasons, not only the storage and computations that I pointed so far, but also from a privacy perspective, right? you'll have a very hard time in reconstructing any faces, license plates, personal identifiers with just this very small number of like events. And some colleagues here at QT and down at U Sydney actually are looking at designing cameras which have this privacy conserving nature built in. So as opposed to doing it on the software side, they'll build cameras which have this principle baked in on the hardware side, which is going to be really cool and very compatible with what we are doing here. So as opposed to basically doing the subsampling, there'll just be the natural output of the camera. And then the second part of the question is, it's kind of, like, could I identify where I am partway in a run? Absolutely. So that is just, me being, for academic purposes, basically showing this distance matrix, which is nicely going from beginning to end. You could start the robot at any point across the traverse, what the robot has previously seen, and you could identify where you are at any given part of the traverse. And what's shown in those precision recall curves as well is that you can even set a threshold such that you can detect if you are in a place that you haven't visited before, which is really important as well, right? You don't want to falsely identify that you have been in a particular place, but you've never seen it previously. And that's feasible as well if you look at the sum of absolute differences and basically set a threshold and say, if that sum is bigger than a certain threshold, then we haven't visited this place before, and you basically should output a unknown. That's feasible. Yep.
Nice. We've also got Maria asking, have you seen or have you used this pixel discrimination technique for other visual tasks like object tracking? Do you think it has potential in such tasks? And she speaks on behalf of all of us. Thank you for your wonderful half presentation for now.
Thanks, Maria, for that. So look, no, I haven't seen it for other tasks. And I don't think it would work for things like object recognition, scene understanding, etc., just because of the nature of the task you have there. I do have a very brief section in the paper basically saying I'm not claiming that this will work on any other tasks other than place recognition. I'm sure there might be some which are somewhat similar and that might work well, but I don't think that object tracking is one of them, just because you'll lose too much information for the tracking task in particular. But no, it's a good one. If you do have any in mind, please let me know. I'd love to try it in other tasks. But I'm like a localization guy, so I stuck with that just because that's what I know.
Something for all the other PhD students.
That's right. Yeah. Awesome, cool. So in that case, I will get rid of this presentation and find my other presentation, which looks better than a white screen, black screen, if I find it. Okay, let me see. Here we go. Perfect. All right. Yes, cool. All right. So now I'm going to talk about the amazing work by some of my students talking about students. And I already preempted kind of what I'm going to talk about now. And that is neuromorphic processing as opposed to sensing. So spiking network-based visual place recognition. So Maya is about to finish up her PhD. She just put her first big draft of her thesis on my desk. So I'm going to read it through later today. Very exciting for me as a supervisor because she's the first student of mine that I had from day one who's graduating under my supervision. So that's super, super cool. So what has Samaya done? Basically, like I came in with this background in event-based vision, and we're like, okay, the natural fit, and Intel kindly sponsored a project of ours, is to look at spiking neural networks. And what I want to focus on, just in the interest of time, is not the spiking net itself, which is probably familiar to most of you. So we based that work on the Deal and Cook digit recognition paper from quite a few years ago now. And we more or less used the network vanilla. But what we wanted to see in her PhD is how we can use those spiking nets to basically enable place recognition, how we can, what's the best way of using them. And the underlying network itself is just basically one example, but we think it's going to generalize to basically any cool network that people in the community will come up with. And it's kind of what we showed in Adam's work, which I'll talk about in a little bit. So basically, what we've done is that we treated place recognition as a classification task in this case. So, in digit recognition, you want to recognize digits 0 to 9. In place recognition, you want to recognize places 1 to n. So the problem is obviously that place recognition is a much harder task, right? That your n is much, much larger than 10, and the representations are much more similar in place recognition as opposed to digit recognition, where you have quite distinct digits. So there's quite a difference here. And the cool thing that Samaya came up with is basically to split the overall task into many, many subtasks and task each of individual spiking net only with recognizing a very small part of the environment. So what we've done is, like we have our reference database with, thousands of images, like now up to 30,000 images. And we train modules where each of the modules only recognizes like 25 places or something like that. And then we just hope for the parallelization capabilities of neuromorphic processors, because each of the individual networks is super small, that for smaller environments, we can, for example, put them on a caporal point, which is what we are currently working towards with Intel. And then basically what happens is that at inference time, so at training time, each network is just training a very, very small subset. At inference time, we feed each of the incoming images. And I always said it before, unfortunately, in this work, it's still conventional images, but we have made progress towards event-based input that I'll show you in a little bit. And then we just feed it to all of those modules in parallel during inference. And then we look at the highest response across all the different networks. And one of the many cool things that she's done is to kind of has this introspection capability where we looked at certain spiking nets, and we estimate the certainty, or the likelihood of correctness of a spiking network by feeding through all the images after they've been trained, and then recording their spike outputs. And basically, in simple terms, what we do is we recognize those neurons that are uniquely responding to just a single place, as opposed to those that are responding to many, many different places, which is not what we want. And then we weigh the contributions of those neurons according to the certainty or of those neurons that they have, and that boosts performance by a lot. The other things that we can do is that we can introduce ensembles. So we can have a single place represented by multiple networks, and then the sequence matching that I previously told you about previously. So what happens there basically? So when we look at those large environments, and Samaya's very first work that I haven't talked about, so that's the very vanilla Deal and Cook, that basically doesn't work in large-scale environments at all. Like we can't recognize like a random chance of recognizing the correct place. If we use this modularity concept, then we increase our likelihood of recognizing the correct place. If you use ensemble, that goes further, and then obviously the highest performance we achieve with modularity and ensembles and sequence matchings. So you guys might ask, what's interesting about this? Ensembles have been around for decades. Sequence matching has been around for decades. What we observed is that the responsiveness of spiking networks to those techniques is much, much higher than the responsiveness of conventional place recognition algorithms, which is really cool. So basically, what it means is that the baseline performance of our system compared to conventional techniques is much, much lower. But then once we add, for example, in this chart here, the ensembling, then we, basically catch up with the state of the art, which also use ensembling techniques. Or here in this case, this graph it's a little bit tricky to read, but basically it's super interesting, I think. Our technique is here in green, and basically what we show is that the increase in performance is the highest when we add a sequence matcher compared to all the other techniques. So, for example, like the baseline performance of our technique and that yellow other technique is somewhat similar. But then after, attaching the sequence matcher, our performance is much, much higher than the others. And vice versa here. For example, this method performs better than ours, this conventional technique. But once we add the sequence matcher, we outperform it. And that's we've shown in many, many different cases. So that's something which is really cool, and I think deserves a bit more attention in the community, or at least look at it. Now, I briefly talked about Adam previously. Adam has been looking into so Maya's work. The big drawback is that it's very, very slow. So it performs well, but because of the ensembling and the high modularity, it's quite a slow overall network. So Adam, funnily enough, is a neuroscientist by training, but his question was, can we trade the biological realism for efficiency to overcome slow training in inference time? So when Adam started, I expected the opposite to happen in his postdoc, but he went this way around, which is super cool. So what happened there is that rather than using rate coding, basically we use temporal coding. So that reduces the number of spikes to less than 1% of the spikes that we had previously. And then the network itself is super simple again, like a 3-layer network. I think it's showed here. We do some pre-processing. And in the first stage, we train the feature layer using just standard SCDP. And then we train, and here are sparse connections between the input layer and the feature layer. And then there's a fully connected readout or output layer where we basically detect the places. And that's using a supervised approach. And what we see is at deployment, basically the same happens. We have this modularity as well. What we see, and those are really cool numbers here. If you look at the GPU numbers, we can train a place recognition algorithm in just like one minute, as opposed to conventional algorithms which go in the order of hours or days to train. And then we can query it at megahertz, basically like 1600 hertz on if you have a GPU available, as opposed to some other techniques which run under 100 hertz. So that's important for compute constrained systems as well, because even if you only have a GPU available, you're still well above any conventional camera frame rate. Or, as I'll show you in a second, as a teaser, we can combine it with event-based vision, and then this is really important as well as deployment on the neuromorphic processor. So what I show you here is basically that, so this is one of the videos that I collected back in the COVID days. What we see is that we do a continual inferencing. So we're basically looking really at the robot deployment scenario now. And there is a threshold shown here. So if you are below that threshold line, we basically say we do not know at which place we currently are. And once we exceed that threshold, we have detected that we are at a particular place. And at the moment, you see that the method says, oh, I haven't been at this place before. And this is because we subsampled the reference places to be only at every 100 meters or so. So if it's in between those 100 meters, then it shouldn't say that it is has been at this place before, because you know it's not contained in the reference traverse. Then what you see is that, you know, every I don't know, 50, 100 meters, I can't remember how often, basically the threshold is being exceeded, and we can continue inference. And I haven't actually included the video here, but what we've shown, or what we will show, and what we will publish shortly, is that you can amend this network such that it can work with event-based input without any intermediate weird other representations directly, and hopefully deploy that. Well, we have deployed it on a neuromorphic processor as well, and I'm being vague here, I'm sorry, but it's not yet published, so stay tuned there, basically. Now, one of my other students, Gokul Nair, recently we put in a preprint on adjusting event camera biases during robotic missions. So what happens with event cameras, obviously, is that, you know, with conventional cameras, as we all know, there have been decades on optimizing and automatically tuning the parameters such as the ISO, the exposure times, etc. With event cameras, as we know, that not yet quite there at that level. And what we know, though, is that it's super important to set the correct bias parameters for downstream task performance, such as visual place recognition or object detection or. And oftentimes it's done manually. So we, you know, people who've used event cameras know how to tune them and what a good event stream looks like. However, with robotic deployments, we don't have that luxury of every single time on startup deciding what needs to be done there. So Gokul, and here we see the stark differences. So with default biases here, we basically see like a super noisy event stream once it comes to dim lighting conditions. And ideally, as I told you in the place recognition task, at least, we want to have the reference and query traverses. So in this case, bright lighting and dim lighting conditions to look the same. And obviously here the conventional images are just shown for reference to really indicate how dark the environment actually was. Whereas if you use the proposed adaptive biasing that Gokul came up with, there's a much nicer and cleaner event representation coming out. So how have we done it? We looked at Toby Delbrook's amazing previous work on event camera biasing. And Toby previously proposed, you know, like individual changes to the event threshold or the pixel bandwidth or the refractory period. And I'm not going to talk you through what they all mean in detail. Please look at our paper where we've got some nice figures and indicate what they all mean. And I think the novelty of Gokul's work is that we couple the fast biasing of the refractory period, which you can basically adjust as you go without any penalties, with a slow biasing in the event threshold and pixel bandwidth. which come at the penalty, at least for Davis sensors, because if you change those biases, then it leads to a burst in, like a spontaneous burst in events that's not meaningful, and you can't process anything, or like basically the output is meaningless in those short windows of bursts, just because how the hardware is designed. And so we basically want to do as frequently as possible this fast biasing, but then once the threshold, in this case we look at the event rate, is exceeded over a certain time period, then we resort back to the slow biasing. And this is what's shown here. Basically, we want to keep the event rate under this threshold, within those bounds. And on the top, we show the different biases that are occurring over time. And this is just the environment, yet another time, our center here. And what Gokul has shown is that this fusion of the fast and slow biasing leads to increased performance, especially if there's a high difference in the brightness condition between reference and query traverse. So check out the paper if you'd like to. And now I'm very briefly going to go away. Before in our chat, Jason asked me, like which packages can I attribute to you when it comes to neuromorphic things? And there's not many neuromorphic ones, but there's quite a few others in the conventional robotics world. I'm just going to talk you through them in the remaining maybe five-ish minutes, and how it relates to neuromorphic as well. So whoever has worked with robotics before has heard of the robot operating system, and I am one of the contributors to RoboStack, which is, according to a very senior prof, taking the horror out of ROS. So whoever has worked with ROS before knows the many pains that you get, but there's this love-hate relationship. And we hope with RoboStack to move it more towards the love relationship than the hate relationship. So for those of you who haven't heard of Conda before, and that's the underlying technique under RoboStack, and one of the things that I heavily use in the neuromorphic space as well, is that Conda is like a package manager. So if you work with Ubuntu, for example, there's apt. If you work with Python, there's pip. So it's one of those means to install packages. It's open source, cross-platform, so it runs on Windows, Linux, and OS X on different architectures as well. And as opposed to, like many people think that Conda is just to install Python packages. That's not true. It's language agnostic. There's heaps of C++ packages, Rust, Go, and so on and so forth. And as opposed to Docker or some other tools, it's not a virtualization. So those binaries, they run natively and fast on your system. And it's also an environment management system like virtualenv, such that you can set up separate environments that don't interfere with each other. And if you mess up one of them, then it's okay, because you can live with the others. And what I'm really, really keen on, and I think, I'm big in, I won't have time to talk about it today, but I'm a big believer in better benchmarking and better reproducibility of papers. Conda, I believe, makes a big step towards that because it enables reproducible science. So we can create files which explicitly say, we need these versions of these packages, and then you will obtain exactly the same results as the author who coded up this maybe years and years ago, which I think is really cool. So with RoboStack, what we basically do is we use those Conda facilities and package those ROS packages. So then you can run it with basically any package in TensorFlow and PyTorch, and a lot of the neuromorphic packages that I'll show you in a second on any platform, which is really, really cool. And you can run it on basically any your PinePhone, your Raspberry Pi, etc. And what I've done, obviously, as being someone who's at the intersection of robotics, vision, and neuromorphics, is that I put a lot of those neuromorphic packages on Conda Forge, such that you can install them on all different platforms with a single command. So it's literally like conda install, and then you just type the name of the package. So while Jason, I don't want to take credit for any of those packages, I'm hoping that I can make the life easier for the Neuromorphic community by easily installing those packages on a variety of platforms without any issues, and in conjunction with a lot of the standard machine learning, deep learning platforms, etc. So that's like the list of tools that I'm aware of. And if there's others that you think are missing, please drop me an email, let me know, and we can collaborate on getting that to work on as well. So the only one that I'm missing at the moment is spikes, because I'm not a JAX person, but at some point when I have a free minute, I will get around putting it on Conda. And I think on the Open Neuromorphic website, you guys point towards those Conda packages as well, which is really cool. So I realized that I'm running out of time, but I want to give you a brief tease of other things that I'm up to. One of my other PhD students, Scarlett, whose videos you see down here at the bottom, she's working on perception of underwater robotics. So she's really driven by the ecological impact and climate change, etc., and seeing how we can monitor our environment over time. So she's done amazing work on using sparse data, because in those tasks we don't have the luxury that we can go on Amazon Turk and ask, randoms to label images, because with those corals, even ecologists can't agree what the particular coral is, but they have a huge impact on detecting and segmenting those corals. So her main work has been on using very sparse data, so similar to what I've shown earlier in the talk, but in the underwater context, and training deep learning models with that sparse data. And then some other things that I'm up to at the top is in collaboration with Nico Sinderhav and Dimitri Miller, looking at some uncertainty estimation and out of distribution detection, which is super important in robotics deployments, because you want to avoid the overly confident estimates that many of those deep learning techniques provide. And I'm hoping that we can make some contributions in the neuromorphic domain on that as well. So I've got some ideas there, so stay tuned for maybe my next talk looking at that. And then just some other bits and pieces. But I do realize I've talked for a long time, and I want to finish up by thanking all my collaborators in the lab and in the wider QT Center for Robotics. I talked with Jason before the talk. It's an amazing crowd in the center. If you are around in Brisbane, please do let me know. Drop by here. I'd be very happy to host you. And just a shout out as well, like if you're interested in anything in the robotic space, anything from control engineering over visual perception, visual learning, to robot manipulation, we constantly have open positions for PhD postdocs, and soon we'll have some openings for external faculty positions as well. And I'd just like to thank the Australian government for funding, as well as Intel, Amazon, and a couple of others. And I think we'll have a couple of more minutes for question if you do have any. Otherwise, thanks a lot for joining in.
Amazing. Thanks so much, Toby. That was, both very extensive but deep. So yeah, appreciate that. We can give a couple minutes to see if the crowd come up with any questions. In the meantime, if I wanted to, actually should mention, when you brought up Conda, I remembered to merge the SNN torch feedstock that I did not update. So thank you for the reminder.
I like it.
Where could we find the notebook material if we wanted to play with some of this ourselves?
Yeah, absolutely. Let me pull up. I'll put it in chat. It's probably easiest, isn't it?
Yes, I think it'll be easiest for everyone tuned in, but we'll copy it in the video description on YouTube once this
absolutely
lives there.
So I will join the connect your YouTube account. I don't know how I'm going to do that. I will send you. I don't want to. Private chat. I'll put in the private chat to you, just because I know it. There is a notebook called Open Neuromorphic Talk. And that's the one, and you can play around with it.
Perfect. So that's showing up on screen. That's in the comment section.
That's awesome.
Yeah, a few people are equally sharing my sentiments on the work that you've done in the chat.
And then obviously, like, I don't know, I'm a big believer in open science, open access. So all of my other works are accessible as well. Just check out my GitHub repository.
Yeah, I feel like we'll need you back for a part 2. Well, this probably should have been 3 parts, and then we'll just have like a monthly Toby fireside chat.
More than happy to do that. Yeah.
No, awesome. I think we can call it there. Thanks.
Awesome. That sounds good.
No, thanks for your time. I'll see you in Japan in a few weeks.
Yeah. Oh yeah, I should have mentioned. Yes, if people are at ICRA in Japan, please drop me an email. And happy to chat anyhow. Check out my website, get my details. Looking forward to meeting you in person finally.
Yeah, I know. I can't guarantee that I'm not going to skip your presentation to go out and explore, but
you got most of it today.
I expect the same reciprocal treatment. No, awesome. All right, man. We'll see you in 3D soon enough. And
all right.
I don't know if I'm meant to have like a fancy music outro like Gregor usually does. I don't know how to do that. Not fancy.
Oh, all right. No, that's all good. Thank you so much for having me. And sorry for the multiple delays in.
I was going to comment I loved watching your brain tick while you were trying to figure out what was the code errors, because I was like, is there a mismatch in brackets or something? Because I always mess this shit up. Awesome.
Yeah.
All right, man.
Great.
Good one.
Cool. All right. Thank you very much. Have a good day, night, whatever it is.
Yeah, right back at you.
All right. Yeah. Bye.